Okay, the next subject is shear stress, shear behavior. And then as I noted last time, so in my lecture note, clicking the tab of my lecture note, you can move very quickly to the different subjects. Okay, so please click the shear section. Alright, so now let's talk about the shear stress. So last time we talked about normal stress. Normal stress means first maybe we have to revisit the normal stress first. So I have a member. I have my member, and then so we wanna imagine a certain cross section. Then in this cross section, this is arbitrary cross section here, and this is a straight cross section. And this straight cross section is characterized by a normal. This is normal, okay? So normal means normal vector. Normal vector. In 우리말 법선 vector. Isn't it right? 법선 vector. So make sure that this cross section is characterized by geometrical information. The direction of this cross section is characterized by this normal vector. Then if you measure the stress on this cross section, its direction is parallel to the normal vector. Okay, is parallel if the traction or the distribution of stress is parallel to the normal vector, then we call it normal stress. Okay, the normal stress. That's why we call normal stress. 수직응력. Then what is the shear stress? The shear stress, let's imagine that we have the same cross section, and then the direction of cross section is still characterized by a normal vector. Okay, the characterization of the cross section, its direction is still same. Okay, and we use the normal vector. But when we measure the traction acting on the cross section, it is direction is not normal, but it is orthogonal. It has a right angle. Okay, 90 degrees. So the direction of the traction is tangential to the surface of the cross section. This is tangential one. Tangential means 접선. Okay, 접선 방향. This is tangential direction. Then we call it shear stress. Shear stress. The shear stress in 우리말 전단응력. Okay, 전단응력. Is it clear? So of course the overall load, the overall internal force may be characterized by an internal force V. This is called shear force. 전단력. So dividing this 전단력, shear force, by the cross-section area, then we can calculate the magnitude of the shear stress. Typically, we represent the shear stress by a Greek letter tau. Okay. For the normal stress, we use sigma to represent normal stress. Or the general stress condition, or general description of stress. Tau is, usually we use tau to represent the shear stress. Shear stress only, okay? Then when we have the shear stress condition, let's imagine that we put a member to the surface of another member using a bolt because the direction of loading is given by the load magnitude is by P. So obviously the direction of load is perpendicular to the direction of surface, isn't it right? The direction of surface is characterized by this direction, normal, the perpendicular. That's why for this condition, how to calculate the shear stress. First we have to consider the area here, the cross-section area of the bolt, the area, and then the shear stress is tau. What is the shear force here? The shear force is characterized by P, and then the area of the bolt, the shear area. And that's how we calculate the shear stress. Is it clear? Do you have any questions for the discussion for the definition of the shear stress? Okay. So now let's take a look at the shear stress in detail. So let's imagine that we have bolt point. Then I have material point here. So, and also let's consider another condition. So here I'd like to detach a material point. Because we have the load in the horizontal direction, if you look at the material point, we must have some kind of traction on top of this material point. And look at the bottom surface. Because of this load here, these guys forms force equilibrium. Okay, force equilibrium. And then we have another force in the left hand direction to form the force equilibrium. Let's check the force equilibrium. The force equilibrium, as we discussed, sum of all the forces in the horizontal direction should be equal to 0. That's the simple force equilibrium, isn't it? So here the magnitude is same, but direction is opposite. That's why we can say that the force equilibrium is completely satisfied, isn't it right? The problem is, if you check the moment, okay, I want to consider this is the reference point here. So let's check the moment contribution to calculate how to calculate moment. The definition of moment is force times the arm length. Here, to calculation of moment with respect to the reference point is first we need to calculate the force. The shear force tau times the acting area. Then we have the force for the calculation of moment. And what is the arm length here? Because we choose the reference point here, then the arm length is equal to 0, which means the moment contribution by this force is equal to 0. There is no moment contribution. But how about this guy? Because we have non-zero arm length, that's why this guy produce non-zero moment with respect to this reference point. Which means I have non-zero moment. Non-zero moment means, according to Newton's second law, that's gonna produce some non-zero, acceleration in the rotation, isn't it right? So that violates the force equilibrium for the stationary the stationary condition. That's why but if you look at my material point, because this is a part of my bolt system, which is in equilibrium, there's also in stationary condition, there's no move, which means we can easily imagine that there is another set of forces. So in the case of shear forces, we need to have a set of shear stresses in the vertical directions too. So the characterization of shear stress is like this. We have shear stress component in perpendicular planes too. Okay, perpendicular planes too. But then what is its magnitude? The magnitude is exactly same. So once you have shear stress in certain direction, okay, then we must have exactly same the shear stress component in the perpendicular directions too. Okay, this is the characteristics of shear stress. Then how do you measure the shear strain? So look, when we discuss the material behavior, we need to discuss stress value. By the way, we need to discuss stress value, and then we need to discuss the strain measurement, isn't it right? So we just discussed how to measure the stress value using the shear stress tau. And then we need to measure the shear strain. The shear strain is measurement of deformation or distortion. So let's imagine that the shear strain is measurement of elongation, the elongation over the length of the member. That's how we measure the normal strain, isn't it? But in the case of shear strain, so we measure the distortion, okay? Let's imagine I have material point, okay, material point, and then let's say this material point is distorted, like in parallelogram. So if you calculate this area of parallelogram, it's exactly same as initial square, isn't it right? There's no change in area. What I mean, there's no change in the volume or the area of a material point. But its shape of material point is distorted. What I mean, 뒤틀린 거죠, distorted. So the amount of distortion is measured by the shear deformation. So we use the shear deformation. Let's say we have initial height of material point h, and it is distorted by angle delta. Then we can measure the distortion by angle gamma here. The distortion angle gamma is calculated by delta divided by h. Okay, provided that the deformation is small. For small deformation. Small deformation problem. Okay, small deformation problem. And then, as given in our lecture note, the shear strain gamma divided by 2 is equal to mathematical shear strain. This is mathematical shear strain. Then what is gamma? The gamma is called engineering strain, engineering shear strain. Okay? 공학적 전단 변형률. 공학적 전단 변형률. The mathematical shear strain is 수학적 전단 변형률. Okay? Then what is the unit? Because to calculate the angles, we divide the movement, the lateral movement by the initial height, the length unit, and length unit. So it's dimensionless, isn't it right? Dimensionless. Do you have any questions? Okay, so now let's talk about the sign convention for the shear stress. Sign convention for the shear stress, and we'll discuss the physical meaning of sign convention later in detail. But in the case of normal stress, the stretch of material is positive. This is a positive shear stress. And then compression of material is negative normal stress condition. But for the shear stress, as I told you, this is characterization of the direction of the surface where we measure the normal. Okay. So if you have, this is the normal, characterizing the cross section. If the direction of traction is the same direction, then this is positive the stress condition. But this is opposite, isn't it right? The characterization of the surface is in the right hand direction, but direction of traction is in the left hand direction. It's opposite. This is a negative, the sign convention. But how about the shear stress? In the case of shear stress, the normal stress, the normal to characterize characterization of the cross section is in that direction, isn't it, right? But if I have shear stress is in tangential direction. Its direction is according to my coordinate x and y. In the positive direction, we have positive direction retraction. Then we call it positive. Okay. So the characteristics of shear stress is what? On the negative side, we must have negative shear stress like this. Because of the angular momentum conservation of shear stress, we need to have the shear stress always in pair. The shear stress like this. This is positive shear stress condition. And how about negative shear stress? Negative shear stress on the positive side, we must have traction in the negative direction, like this. Okay, because the shear stress should be opposite. On this side, we need to have traction upward, like this. This is negative shear stress. Okay, this is characterization of the sign convention of shear stress. Do you have any questions? So again, the relation between the shear stress and shear strain is linear too, as long as we discuss the material behavior in the linear elastic range. The shear stress is proportional to the shear strain, and the proportional coefficient is given by G. And this proportional coefficient is called shear modulus. Okay, shear modulus. 전단 계수. We call it 전단 계수. The shear modulus. Okay, shear modulus. Or 전단 탄성 계수, same meaning. Okay, 전단 탄성 계수, 전단 계수, same. And there is, one-to-one relation between the elastic modulus or Young's modulus E and the shear modulus. As you see here, the shear modulus G is given by the elastic modulus and the Poisson's ratio. So what does it mean? Shear modulus is not an independent material parameter. So once we determine the elastic modulus and Poisson's ratio, we can calculate the shear modulus using this formula. So at this moment, maybe you want to memorize this equation. So we will discuss the physical meaning of this equation in detail next time. Okay. So again, the unit of shear modulus should be the same as stress, because the unit of elastic modulus is same as the unit of stress, the force per unit area, isn't it, right? Because the Poisson's ratio is dimensionless constants. That's why the unit of shear modulus is same as the unit of elastic modulus. Let's do an example for the calculation of shear stress. Okay, look. So I have a puncher here. So I'd like to make a hole using this puncher. So let's try to calculate the shear stress. So here, first we have to identify what's the shear area, isn't it, right? The shear area. So first we have to calculate the shear area. We need to consider thickness. The shear area is the thickness of the plate, and then the perimeter of the punch, isn't it, right? So pi is d of the punch. Here the thickness is given by 8 millimeters, and then the diameter is given by 20 millimeters. The shear area is 160 millimeters times pi. Its unit is millimeter square. So what is the load? The load is given by 110 kilonewton. 110 kilonewton. So now let's try to calculate the shear stress. The shear stress is equal to load P divided by shear area. This is equal to 110 kilonewton means 10 to the power of 3 Newton. And then 160 times pi times millimeter squared. The milli means 10 to the power minus 3, isn't it right? 10 to the power minus 6 meter squared. Then what would be the unit if you calculate these numbers? The unit is, if you calculate these numbers, the unit is Newton per square meters. This is Pascal. Do you remember the Pascal unit is too small? That's why in structural applications, instead of Pascal, we use megapascal. That's why for typical calculation, it's better to use, Newton unit for the force and the millimeter unit for the calculation of geometric information, length and area. So if you do that, if you follow this, then what? Let's try to calculate the shear stress in the unit of megapascal. This is 110,000 Newton and then 160 pi millimeter square. Okay, look at this. The millimeter square is the milli square is 10 to the power minus 6, as I mentioned here. So if you move to the denominator, the numerator in this operation, it becomes megapascal. So just calculate this number, then we can obtain the result in the unit of megapascal. So for the force, we want to use Newton. For the area, we want to use millimeter square. Then we can obtain megapascal very easily. Okay. Then let's consider another example. So here I want to calculate the shear stress of the bolt or this pin. So then how do you do that? So first we have force P here, and then we need to identify the shear area. So if you consider force equilibrium, because only I'm using the part of my iPad screen, that's why sometimes it is difficult to recognize the active area. Let me change the color here. So I have the strut, and make sure that this strut is subjected to load P, and then it is resisted by this pin here, isn't it? Pin. So it is resisted by this pin. So if you look at the side view, and then the load transmitted to the strut is resisted by this pin, the shear area is what? The shear area for the pin is equal to 2 of the cross-section area, isn't it right? The 2 times of the cross-section area of the pin. Because we have 2 surfaces. And then of course the load is given by the force P. P. This is shear stress for pin. Is it clear? Okay. Then how do you calculate the shear stress of the bolt, the anchor bolt? So how many anchor bolts do we have? We have 4 different anchor bolts. So the area of shear for the anchor bolt is 4 times area of anchor bolt. Isn't it right? Anchor. Then what is the shear force? The shear force is what? We need to consider tangential force components. So P times cosine 40, isn't it right? So P cosine 40s, isn't it? Then we can calculate the shear stress of the anchor bolt using tau of anchor bolt is V divided by the shear area of the anchor bolt. Do you have any questions? So today we discuss two different subjects, the material law and then the shear stress. So let me stop my lecture here. The next time we'll talk about the bearing stress and then stress component by equilibrium probably. So if you have more time, then maybe we can visit the allowable stress too. So as I mentioned, I break the lecture note by the sections. So if you are interested in these small sections, please search for the title of these sections. You can find a separate individual lecture note. Okay, see you next time.